Hey guys, today we will be proving the Cauchy-Schwartz uncertainty principle, which says our squared covariance cannot exceed the product of our individual variances of random variables. So to prove this, we will be starting by defining a random variable z as the mean squared version of our random variables as like a linear combination of the mean squared versions of our random variables for for all c in R. So we just define some constant c, and by this we have that our expectation of z squared will always be greater than 0, just because it is some random variable squared and all squared numbers are positive. So continuing on that, we have that 0 is less than or equal to our z squared, which if we write it down, it's x minus mu x minus c y minus mu y whole squared expectation. And kind of just factoring this whole thing out, we have that this equals the expectation of x minus mu x squared minus or plus c squared y minus mu y squared minus 2c x minus mu x y minus mu y. And so by linearity of expectation, this is just the expectation of x minus mu x squared plus c squared expectation of y minus mu y squared minus 2 times the expectation minus 2c times the expectation over xy of x minus mu x times y minus mu y. And so now we can look at this, and this is just our definition of covariance. This is just our variance with respect to y. Now this here is just our variance with respect to x. So this whole thing can now be simplified into variance of x plus c squared variance of y minus 2c times the covariance of xy. And so looking at this, we can kind of do a little trick and say that since c is some arbitrary constant in our reals, we can just take our c to be the covariance by the variance of y, almost as a correlation coefficient in some sense between x and y. So taking c to be that, we have sigma squared x plus covariance squared times variance of y squared by variance of y to the fourth minus 2 times covariance by variance of y times covariance again. So simplifying that out some more, we have variance of x plus this cancels, so covariance by variance of y minus 2 times covariance squared by variance of y. So these covariance squared by variance of y and covariance squared by variance of y are the exact same thing. So 1 minus 2 is minus 1. So we have now variance of x minus covariance by variance of y. And given we just took some random variable z and squared it and said that it was positive, this whole thing is now greater than 0. So we can do some remarks here saying that this expression is greater than 0, and then therefore our variance of x is greater than our covariance squared by our variance of y, and then times our variance of y again, times our variance of y on both sides, we get that our covariance squared is less than or equal to our variance of y times our variance of x, which is the exact same as the Cauchy-Schwartz uncertainty principle for global populations. And if we wanted to do the sampling version, we would just go through the whole thing, and every time we had an x, we would change that. Every time we had a mu x, we would change that with x bar n, and every time we had a sigma, we would change that by sx. And then this is for global population. This is the uncertainty principle for global populations. But if we wanted to derive the same thing for samples, we would do the exact same thing, except use x bar n instead of mu and use sx instead of sigma x. So yeah, these are equivalent, but they're connected via the sampling stats theorem. And so now we have just proven the Cauchy-Schwartz uncertainty principle for global populations, and thank you.